to Ali.
Okay, I think I have a few housekeeping items that Meta wanted me to share with folks in the room. So one is, like I mentioned, we are live streaming, so hi to all the live streamers. Great to have you here, and recording all sessions. For those that are non-Meta employees, make sure you bring your badge back tomorrow, and you enter through lobby 14, which is where you all hopefully did. You'll do the same thing tomorrow. Just remember to keep your badge and bring it back tomorrow. We do have a conference room available for ad hoc discussions if you need some quiet space to sit and work. It's right across the way. It's called Chips and Salsa. So that room is also ours to use, so feel free to drop in there if you need to. Folks that took a ride share, if you are planning on leaving before 7, you need to take the tram back to the ride share area. If you're going to stay for the party, you can get a ride share from here after 7. And finally, tonight, we hope you stay for the conference party. It seems like it's going to be a really nice day weather-wise, and we are doing it right out here in the garden. So we hope you can stay and hang out and chat with the Velox community. I have to say thank you to the conference committee. These things are quite hard to pull off behind the scenes, and so across Meta, IBM, and NVIDIA, there were a bunch of people who helped put this together. So thank you to all of them for the next 2 days of hopefully really awesome things around Velox. Finally, thank you to all of you. Our community is amazing, whether you've contributed, you've mentored, you reviewed, all of these things. You're the reason why we're seeing such great numbers and why this community works. So thank you. We always like to end with a little what's next. If you remember last year, we said maybe we would be going to China, and we did it. So what's in store for this year? Maybe in a VeloxCon Europe, maybe another VeloxCon China. So stay tuned. Oops. We are really excited for those events and to keep growing the community worldwide. Okay, with that, let's officially kick things off with our first Velox session keynote of the day from Pedro. So Pedro, why don't you come get set up? Thank you.
All right. Yeah, so let's get going. I'm happy to kick off the technical sessions. I'm super happy to be here at VeloxCon, hosting a bunch of people from Meta and the industry. So thanks for joining. So when I put together this talk, I was trying to give an overview about Velox and what's happening, but we're also going to have a lot of talks that will get into more detail. So I tried to take a step back and talk a little bit more kind of high-level workloads, where those workloads are going, some changes that are happening because of AI, and talking about not just Velox, but some of the other components we've been developing, other things that we open source recently. So kind of focus on not just on Velox, but things that are happening around the Velox sort of ecosystem. First, again, just want to thank everyone for taking the time for joining us. I know it kind of takes taking 2 days out of your time is not it's not easy. So thanks for joining. It's great to see so many familiar faces. For those who have not joined every single VeloxCon, the very first VeloxCon was actually held in this room. I'm wearing the T-shirt, so it's kind of nice to be back. I think it was back in 2023. Now we're in the 4th VeloxCon, and like Ali said, we're kind of 5th because we held VeloxCon China, which is kind of a side charter. Hopefully going to do this year again, but thanks everyone for joining. Just kind of how when we started Velox, what the sort of the world and the workloads in Lakehouse look like. So we had what people used to call, or what we call it nowadays, the analytics lakehouse, which is essentially a lakehouse that was built and optimized for analytic workloads, like things for business intelligence and decision making, right? So we had workloads around dashboarding, data exploration, generating reports, kind of slicing and dicing dashboards. Another big use case was A/B test experimentation platforms, right? So people, like, they want to run experiments at large scale. You go, you change the color of your button, and you want to create large data cubes that let you slice and dice the data and see, is engagement going up or down. So there's a lot of interesting use cases from this analytics lakehouse back maybe 5, 6 years ago when we started Velox. If you really take a step back, maybe a 10,000 feet view of this lakehouse, you see essentially there's a shared storage. You have some ingestion pipeline that usually ingests kind of logs from applications and web logs. And there are two main workloads. One main workload is just batch, right? So you have this idea of running large-scale pipelines to generate data sets that maybe trigger another pipeline that generate new data sets, right? So just this idea of kind of keep processing and curating the data pipelines. That's usually where people use Spark in the industry quite a lot, but of course there are many other tools. Another important use case was just the kind of using this data or taking this data out of the warehouse, right? So just kind of the analytics tool that let you kind of slice and dice the data, power dashboards, and they usually optimize a lot more for latency, right? On the right side, I think for this community, like many people use Presto, like although you can also use Presto for batch, you can also use Spark for interactive workloads to some extent. But those are kind of the main workloads, and when we started Velox, those are the things we focus on. One side was Spark integration, the other side was Presto integration. Fast forwarding to today, we have what we are calling the AI Lakehouse, right? Which is essentially kind of the same. But it's a lakehouse that is optimized for AI workloads. So now we're in a world where AI is the biggest consumer, both in terms of data, in terms of compute. That means that most of the data and most of the tables you have on the warehouse, they're actually training tables, like to power training. And most of the compute you have is actually to curate those tables and to feed those tables into trainers. Right? So whether we like it or not, AI is the biggest customer, right? So we need to continue relevant. We need to continue sort of optimizing and evolving for this type of workloads. And now instead of 2, we have maybe 3 workloads. So we still have a batch, the ETL, the data preparation, except that it looks slightly different, right? So now for the batch workloads, we now call training data preparation, which is, like I said, most of the batch pipelines are actually preparing data sets for training. People still use a lot of Spark for doing those things, but there's some kind of differences between what you use for training data preparation today and what you used to use for analytics warehouse. One of the main characteristics is that usually training data sets, they're a lot wider. So usually you have a lot of features. Those features sometimes are large maps, and those maps might contain sequences. So the sort of the shape of those tables really changed. So just using vanilla Spark or kind of vanilla engines that were developed for analytics back in the day, like it's usually not very efficient. One of the main workloads you have on training data preparation is this idea of feature injection, which is when you have your training data set and you calculate a new feature offline, how do you inject this feature in the training data set without having to rewrite the entire table? So this is a very recurrent and very common workload that you need to support very efficiently. So last year we had, actually my talk was a lot focusing on that. I see that Konstantinos is now in the back, and last year he also had a talk about like how to use PySpark to accelerate some of those workloads. So there was a lot of discussions last year about this. And of course, as you're kind of moving data that is really, really wide, you want to make sure that you kind of read and you decode and you transform this data as few times as possible. So if you have things like operations or cardinality reducing, like filters or joins, like you want to lazy materialize things as much as you can, because materializing data that is really wide is actually super expensive. Right? So there's a lot of tricks on how you push lazy materialization further. We also had this idea of encoding preservation, which is if you're moving a bunch of data from one table to the other, like how can you sort of minimize the amount of transformations that happen to this data? For example, if this data is already really packed and encoded in the source table, can you actually move this to the target table without decoding and without decompressing? So there's a lot of kind of tricks there. If you're interested, we kind of talked about this last year. Right. Second one is interactive workloads. This is kind of the same, not much different. The main difference is that now, well, as we all know, we don't have as many humans interacting with those things. You're mostly interacting through agents. Query patterns from agents, they're not as different. There's this discussion that we usually have a lot more, right? Because those agents are issuing a lot more queries. So there's discussions on how do you cache, how you can potentially pull this data locally so you can enable agents to slice and dice this data locally. So you have a much higher volume of queries. There's also discussions on how to enable kind of more advanced types of analytics, things like vector search, so you can calculate similarities and things like that. There's going to be a bunch of talks. Zichen has a talk about vector search. But I think this is one of the kind of the second workload is just essentially agents looking and transforming and slicing and dicing this data on behalf of humans. But then we also have this third workload is that, especially for large-scale warehouses, you're putting this data in the warehouse and you're transforming because you actually want to train large-scale models. Right? And this is something that essentially didn't exist before. This has been one of the main focuses of the Velox team in collaboration with the many other infrastructure teams at Meta. And I have a couple of slides to detail and to focus a little bit more on what happens inside this sort of data loading for training. All right, so what's training data loading? So training data load is essentially kind of a compute engine, but the destination is not a table. The destination is not pixels on a dashboard. Like the destination are trainers. Trainers are basically programs that usually use libraries like PyTorch or TensorFlow, right? So they ingest batches of data. And you go through this training process that does a bunch of matrix multiplications and things like that. And in the end, you generate a trained model. Right? So essentially, like you're pulling and consuming the data, doing some transformations, and feeding this data into processes that do the actual training of models. It is a compute engine, but it has some particular characteristics. One of the main things that it's a little bit more of a mental model than just kind of specific details of the engine, but the main optimization goal on training data loading engines are the fact that you're optimizing for GPUs. So the main thing you want to optimize for is you want to make sure that GPUs are always fed and you're not starving GPUs because you have very few GPUs and they're expensive, right? So usually some other engines you optimize for efficiency, maybe you optimize for latency, right? Like here, I mean, you also care about those things, but you care a lot more about making sure you have this kind of a fixed stream of data in the GPUs. You have two main use cases for those things nowadays. On one side, you have generative AI, things like LLMs. In this case, you do a lot more of kind of the data cooking. All the preparation happens offline. So like we discussed, like a lot of that stuff happens in Spark during training data preparation. And at training time, usually the transformations you do are a lot simpler and more uniform. On the other hand, when you're training recommendations models, they're usually a lot heavier in terms of pre-processing. Right? So as you are reading this data from the warehouse, you usually do a lot more sort of post-processing or last mile processing before you feed this data into trainers. There's a lot of reasons for that. One of the reasons is that you're usually pulling data from different data sources. Like so sometimes you need to join, kind of stitch data together. There's a lot of workloads on just kind of extracting labels and extracting signals from raw data. Just we can think as a bunch of kind of lambda functions and expressions that generate a binary label. So a lot of that you want to do as you load data on the trainers because people are doing experimentation and they want to try different things. They want to try one feature, it didn't work, they want to try something else. There's also this process of kind of encoding features. There's a lot of feature engineering, like normalizing things and reducing dimensionality. Usually when you're training recommendation models, you have high cardinality, multi-categorical columns and features. And those things usually require very large embedding tables. They're kind of hard to manage. You cannot just copy them everywhere. You need to shard things. So sometimes you need to shuffle the data. So there's a lot of complications. So usually what you see in the architecture of those systems is that usually when you're training LLMs, you do all this preparation beforehand and you load data into storage. So when you're training data, you're essentially moving this data from storage directly into trainers. While for recommendation models, you have this data in storage, but as you pull this data for training, you do a lot more pre-processing to a point where those things usually cannot fit on the actual training servers that have GPUs because of what we just said, right? If you have too much workload, if you get bottlenecked on CPU on the trainer, then you're going to be starving GPUs. So the idea is that usually for those systems, you disaggregate compute. So you have this tier of workers between trainers and storage to kind of absorb this kind of high amount of compute. And then, of course, the more models you have, the more data, the more kind of complex those transformations get, the larger this tier gets. Right? So if you look at this kind of tier of compute, it's actually a very substantial part of compute, right? It's actually comparable to the other two workloads we just mentioned, if not larger. So yeah, great. So we need to load data into trainers. Can we just run Presto or can we run Spark? You have table scans, you have filters, you can do merge joins, you can do all those things, and that should just feed to trainers. And you're kind of good. So that's a lot of discussions we had in the beginning, like especially when sort of data people were getting into the space, and it turns out that many things are very similar, but many things are kind of not quite the same. Some of the interesting things here is that when you load data in trainers, batching really matters. So usually when you're training your model, you have a very specific batch size, let's say 1,000 training samples, or 2,000, or 4,000. And the batch needs to have the exact same size. Right? So usually when you're processing things inside engines, if you're filtering, if you have joins, you can get batches of all possible sizes and kind of aggregating those things. Like most operations are kind of associative and commutative, so batching doesn't really matter. Like here, it really, really matters. Ordering of the data matters. Depending on the order you feed this data into the trainers, you can get a completely different model with different qualities. So usually you want to specify what's the order of your data, how do you kind of scan different days or different hours in the day, how do you kind of mix this data inside batches. So not just the ordering, but the data mix you have inside those batches really matter. So sometimes you want to have in the same batch, you want to have data for today and mix with 50% of data from, I don't know, last week. And those things really matter, and like I said, if you don't do that, your model might have very different characteristics. And those are things that you cannot even express in SQL, and they really, really matter here. Synchronization here really, really matters. So the way this thing works is that usually you have a cluster with many, many GPUs. And for every single pass of your training process, you need to fit one batch into one GPU. Once you have all those batches, you do forward pass, you do backward passes, you need to shuffle data in between. So if you have one GPU struggling, or if one batch is delayed, you end up starving the entire cluster or all the GPUs assigned for that job. So synchronization in this case really, really matters, right? So you want to make sure that you have all of your sort of distributed queues optimized so that you make sure that the training process is going without starving GPUs. So all those things are kind of different requirements if you look at how traditional compute engines work. Data completeness in this case doesn't matter as much, right? While when you're running analytic queries, you need to process every single record because you need to guarantee that the results match, right? Because otherwise, maybe, don't know, your revenue results will be missing $1 million or whatever that is. Here, in some cases, if you drop some data on the floor, it's not that big deal. In many cases, for example, if you don't have a batch with the right size, you rather just throw this batch away than kind of, trying to train with an incomplete batch. Right? So the requirements are kind of slightly different. There's some other kind of particularities that are not very different from compute engines, but also worth calling out. Usually when you're running, especially when you're training large-scale jobs, those large-scale models, those jobs might take quite a while. Right? So it can run for many hours, for many days. And you want to checkpoint those things. If something goes bad, you need to be able to kind of roll out to the last checkpoint. Many compute engines can do checkpoints across stages. Like here would be a single stage, and you need to checkpoint that specific stage. So some engines do that, but it's just something worth calling out. Again, going back to not starving GPUs, depending on how much processing you do on those workers, you might need to scale those things up and down. Right? So you need to make sure you can do this very efficiently to make sure that the stream of data going into the GPUs are kind of uniform. There's also the interesting part that, especially for recommendation models, data freshness really matters because users, things that users like are always changing. So you go to Instagram, you go to whatever application, you like cat videos, next day you like dog videos. And so you need to make sure you have an online way to train and to update the weights of your model. All right, so it's a completely different thing. Do we need a completely different engine? Kind of. So sort of the orchestration, the platform is different, but the processing you do inside those things are very similar. So if you look at how you scan tables, how you push down filters, how you decode files, that's all the same. How you kind of execute expressions, how you express UDFs and filters and joins, like all of that is just the same, right? So while we cannot just use Spark or Presto or whatever engine for training, we can use those components, right? So it just happened that we have this library which kind of extracts that from the engine and lets you use those operations in different contexts. Not going to go too deep into details here. If you're interested in kind of more details of how this platform works and how those things are getting integrated, Elodie has a talk later today. She's probably here somewhere. Stay around. It's a great talk. So what happens inside those workers? Like when you're training, when you're moving this data from the storage into the trainers, Basically, you use Velox or a Velox task to pull this data from out of the warehouse. You decode this data, you do some joins, you filter, and all of that. At some point, you generate Velox vectors, right, which is this way of representing data in memory. You need to convert that into tensors before you pass into the trainer, which is a PyTorch or a TensorFlow process. Oops. Dismiss. So what's a tensor, right? So tensor, I think we always joke inside data infra teams that tensor is just some AI jargon to kind of keep data people away. When we started doing those integrations, there was a lot of discussions of like, no, we can't use this, tensors, right? Like kind of, no, something that's supposed to scare you. Of course, there's a nicer mathematical formal description, but in the end of the day, it's a buffer. It's a multidimensional buffer that lets you handle multidimensionality, like has APIs for you to sort of slice and dice dimensions, like do strides and things like that. But in the end of the day, it's just a multidimensional buffer, usually contain scalar numbers, mostly floats, but you can have integers and things like that. It's not like Velox that, or things like Arrow, where you can actually have arrays and maps and, and things like that. Usually, tensor is just a multidimensional buffer of scalar numbers. Well, so sometimes those tensors are really large, right? So you can have many, many dimensions. Like a single tensor might have gigabytes of data. In some other cases, you have tensors that are quite small. They represent a single dimension or a couple of dimensions, right? So kind of there are tensors and tensors. Of course, some of the tensors you use for training, like they're very different and they have very particular characteristics. Some of the tensors you use in this process, they're essentially like something like an arrow buffer or a Velox vector buffer. To transform those things back and forth, usually we have a process that we call feature encoding. So you're pulling this data out of the warehouse, you get this data out of Velox. So to transform this data into a tensor, you have to sort of encode this tensor. There's a lot of questions on how do you do that? What are the different types of tensors you support? How do you configure this operation? So for example, if you're reading like a scalar column with floats, it's kind of easy. What if this column is actually a map? Or what if you have a map with an array inside? Like how do you do those mappings? How do you map those things into tensor dimensions is actually something not super straightforward and not well defined. I would say it's even not defined anywhere. So there's another project on the same sort of Velox ecosystem that we started developing internally called AI11, which is something that's supposed to kind of standardize a lot of those conversions between vectors and tensors. It's something that exists, but it was just kind of scattered through a bunch of code bases, like not in a very consistent way. So the idea here is just provide a canonical implementation of feature encoders and canonical implementations of sort of different tensor shapes and tensor layouts. So this basically, it doesn't re-implement the tensors themselves. It's just a library that wraps around PyTorch A10 tensors. A10 is the kind of the internal C or C++ library that handles tensors inside PyTorch. So A10, A11. So in A11, you can have representation of different types of tensor, dense tensors, dense and sparse features. You can have encoding, so you can have tensors representing kind of duplication of things like dictionary encodings. We provide kind of basic batching-related operation. Remember that discussion that batching really, really matters, right? So we can have this sort of semantic layer on top of tensor, and you can still sort of split and concatenate them to sort of give you more flexibility on how you organize your compute. It ships with a feature encoder. Feature encoder, again, there's a discussion that batching really matters. So as you encode data, you can actually specify the size of the batches you want to generate. We're also adding features like encoding preserving. Like in many cases, you're reading this data, and the data is already kind of really packed as a dictionary. So as you do the feature conversion, you want to sort of maintain this encoding, right? You don't want to unpack this entire thing and then pack it again downstream. All the operations we are adding to A11, they're built based on PyTorch operations, which means that this is sort of portable between CPUs, GPUs, and whatever other accelerators PyTorch supports. So one way to reason about feature encoder is just making a parallel with table writer. So it actually happens, I mean, not exactly the same, but there's a lot of similarities. So when you're encoding features, you have a process that kind of keeps consuming data out of your Velox tasks. You keep consuming, you keep batching until you reach a certain size. You encode this data in some special format, and then once you hit this size, you kind of produce something, right? Just happens that when you're writing tables, you're accumulating vectors until you reach a stripe size, and then you encode things using Parquet streams or C streams or whatever file format you have. You generate a buffer, and then you sort of write that to storage. Here, I mean, kind of the same. You accumulate until you have the batch size. The encoding is using A11 encoders, and then you produce this batch that you pass to the GPU for training. Right? Like the data flow is the same. Another interesting part is if you look at compute, so of the Velox part, which is sort of stitching data back together, filtering, applying data transformation, is actually just kind of half of the workload. So what happens is you stitch this data together, you use something like A11 or some way to encode those features into tensors. And then there's a lot of processing, a lot of compute that happens in those tensors, which are more kind of numerical transformations, normalizing features, sort of reducing the dimensionality and a bunch of things. Why do those things run into tensors? A lot of reasons, but one of the main reasons is because those transformations are really close to the model, meaning that you need to apply usually the exact same transformations during training and during inference. And during inference, you don't have like a Velox batches, you have other things. So there's a lot of kind of transformations that happen after the feature encoder process. That if you really look into that, is a bunch of tensor transformations, and they look very sort of AI and sort of exotic. But if you kind of just really what they're doing is basically compute, right? So you can understand that as expression evaluation, kind of the same trade-offs. You have columnar buffers. We can do vectorization. You have virtual dispatches. You can JIT compile. So it's kind of the same. Instead of expressing those things in SQL, you express that in Python using PyTorch. Instead of Velox vectors or arrow arrays, you have tensors, right? But if you kind of remove the noise, it's kind of the same. So there's a discussion that, well, if it's a tensor, just move to the GPU and then we're good with it, which is something we're working on. The idea is that, well, not quite, like we discussed in the other slide, there are many, many types of tensors. If you have really large tensors and very kind of chunky operations, it's great. You submit your CUDA kernel and you're great. If those operations are over small batches and they're actually quite cheap, kind of just mapping this to CUDA kernel is not efficient, right? So there's a lot of discussions on how do you map and how do you pack those things. Just happens that we took a head start on those things with the Velox wave a couple of years ago. I think Ori is not here yet. So now there's a lot of discussions on what can we reuse from Velox wave, right? This idea of doing that for sort of expression evaluation and query processing in Velox, and how can we map this into sort of tensors and PyTorch. So Ori has a talk tomorrow that's going to give you all the details about this thing. All right. There's a bunch of stuff we're doing around compute. We have those 3 main workloads. What about storage? Like, is the storage the same? Are there new features? So it also turns out that the way you store this data is also not very efficient if you just use traditional sort of storage and file formats and table layouts that were developed for analytics. Like I said, the data is usually much wider. You usually have many, many features. In many cases, because you want to add features and remove features very frequently, you don't map those features as top-level columns, right? You just kind of plumb all of them inside maps. There's a bunch of discussions on how do you support maps efficiently, how can you sort of project individual features very efficiently from maps. So we ended up creating this new sort of mapping encoding called flat maps. There's a discussion that sometimes those features actually very long sequences of user interactions, and sort of the longer those interactions, the better, right? So the data is really, really wide. There's also discussions that there's a lot of transformations that happen during this training data loading process that could be potentially cached. So if you want to cache or if you want to materialize, how do you map different tensor types to file formats? So there's a lot of kind of interesting questions on the storage layout here. A few years ago, we created this new file format called Nimble. It has a few interesting characteristics. It has this idea of supporting cascading encodings, right? Which is it can take an encoded stream and then put another encoded inside another encoded stream, and you can do those things hierarchically. It's very interesting because it lets you do encoding over kind of nested structures, right? So you can take entire vectors or entire maps and you can deduplicate them, right? If you can kind of cascade those things. So it supports cascading encodings. There's also this idea that because AI is growing so fast, like we're probably going to come up with kind of different ways to encode streams on disk, right? So like just making sure that the way you build encodings inside file formats is extensible. Because, again, this thing is really, really wide and denormalized. It just goes up to a point, right? You're going to get to a point where you can only fit a single row inside a stripe or in memory, and then, none of the vectorization things make a lot more sense. So, of course, there's a lot of interest in how can we actually normalize those things so we can kind of move the bulk of features somewhere else, make the training tables skinnier, and then, of course, you need to normalize. You need to join them and stitch them back together on the fly. There's a lot of discussions on like how do you support this in file formats. We ended up adding support for dense and now cluster and now dense indices in Nimble. There's a discussion that when you have indices on the file, how do you stitch them back together? So in Velox, we ended up also adding support for things like index lookup joins and index table scans. There's a lot of new features we're exploring inside Nimble. Like we discussed, how do you map tensors? What are the tensor types? How do you encode those things? How can you potentially have indices for vector search and things like that? So if you're interested in this space, we're going to have a talk later today by our very own Mung, who's kind of a famous engineer superstar. After VeloxCon, we realized that he's a super famous engineer. I don't know if he's here yet, but he's going to tell you all about storage, what's happening on the file format layer, what's happening on the table on the table layer, things like iceberg support, Pymon support, and things like that. All right, the last thing I want to quickly talk about is front end. So we're getting to a point where looking at the three main workloads, which kind of cover the bulk of compute, all of that is converging to Velox. It has already converged, like Akash mentioned earlier today, from the sort of interactive analytics, all the Presto workload is already running on Velox. We're now converging in Spark, we're converging training. So what's next? So a few years ago, I think it was 2023, we put together this vision paper. We published that at VLDB, which is this idea of like a vision paper that you should actually look at those monolithic compute engines and you should decompose them into components so that it would give you a lot more flexibility in kind of reusing those components. You can reuse them, it improves engineering efficiency. We don't need to re-implement the same things over and over. So we actually made a lot of progress on that. So this was sort of the kind of the data stack we proposed on that vision paper. Of course, this is a lot more from a query processing perspective, right? But you have a language, you have sort of a way to represent queries, like this IR or logical plan and physical plans. You have optimizers, execution, and runtime, which is sort of the environment where you run those things. We're getting to a point where we were able to converge execution and Velox. So I think not just internally, but if you look across the industry, like, Velox is becoming pretty pervasive. Right? So this part is good, but what we ended up seeing is that if you look at the front end, and by front end we mean sort of the language layer, the optimizer, and the IR, we kind of have similar problems. So there's a lot of things that we end up re-implementing, like for example, things like if you need support for Pymon or for Iceberg, you need to sort of implement the metadata layer on every single engine. If you now need support for indices and index lookup joins, you need to extend every single optimizer. So there's a lot of kind of duplication of work as this part that maybe is similar features in different systems. They are kind of inconsistent. They don't act in the exact same way. Some systems have features that are not available in the others, and then for users, it's really hard to reason about. The other big problem with this is that language is, or kind of the way we develop compute engines is that language is coupled with execution. So it means that usually if you want to use Spark, you need to write things using Spark SQL or whatever Spark dialect or PySpark. If you want to run things in Presto, you need to use Presto SQL. So usually if you want to use a specific engine, you need to write or you need to rewrite your query using that specific engine dialect and semantic, which is, not great. So there's no very good reason to do so. Like if you look at execution perspective, runtime, there's really nothing particular, and no good reason why that should be kind of tightly coupled with the language layer. So what do we do? What's the answer? Well, we're going to compose the front end as well. So we're getting to this. So we started this project called Axiom a couple of years ago. It has a language layer. It has an optimizer. We support Presto SQL, Spark SQL. We also recently added a new Spark Connect implementation that supports PySpark on the same stack. We call that Collagen, if you understand why it's called, what's named after protein. But yeah, so there's this new stack called Axiom. There's a lot of benefits, better reusability, engineering efficiency. It lets you support many languages. We can build the exact same stack and reuse for multiple languages and multiple dialects. And this idea of sort of decoupling language and execution. Not going to give you too many details. The very next keynote by Masha, she's going to give you all the details and talk about where we are, what's the vision, what's the architecture, and how we're making progress. All of this is also open source. So just wrapping up, of course, data is more critical than ever. There's no AI without data. You need data to train your models. You need data for agents, right? So not just data, but we also need very efficient ways to kind of continue processing this data. So our experience is that composable data systems, they have been really helping, right? A lot of the things you do inside the engine are the same, but the way you put those engines together, they're usually very particular to the use case. Right? So this is something that over the years we saw that was really kind of the best or the winning architecture, like just looking at common components, extracting them out, making sure they're really high quality, they're very efficient, and reusing across engines. Collaborating with the open source community, making sure all those things are open source, working with other companies, that has been also super helpful. We intend to do more of that. Of course, the main project was Velox, but we're also making some good progress with Nimble, now with Axiom, Collagen, Velox Wave, A11. It's not open source yet, but we have plans to open source it later this year. So this has kind of been the winning strategy. So yeah, thanks everyone for listening. At Meta, we usually like to end things with this journey is 1% done, to give this idea. There's always a lot more going on. Thanks for joining, and hope you enjoyed the program. Thank you.